All right, so we were talking last time about carbonyl chemistry. Carbonyl compounds are electrophilic. We're going to be talking about a lot of different carbonyl compounds, and so we want to have a good understanding of reactivity. Why is one carbonyl compound more reactive than the other? We can memorize the order of reactivity, but that's less satisfying than actually understanding the order of reactivity. It'll enable us to make more complicated decisions when we get more deeply into carbonyl chemistry. So, relative reactivities depend on relative stability of each acyl derivative, so we're talking about a combination of inductive and resonance effects. So we do have two factors here. We have the inductive effect. Oh, this thing just a little touchy here. Okay. So we have our group L. We're talking about the compounds, the carbonyl compounds that have group L, so type 2 carbonyl compounds. As L becomes more electronegative, it pulls electron density away from the carbonyl. That makes the carbonyl carbon more positive and therefore more electrophilic. But we also have an opposite effect, which is the resonance effect. And for the resonance effect, it's opposite because now the leaving group, the group L is feeding electron density into the carbonyl carbon, adding electron density. So that's going to make the carbonyl carbon less positive. Less positive means less electrophilic. So how are we going to decide which one's more important in which case? Okay, so we're going to have to weigh the two. In some cases, the inductive effect is more important. In other cases, the resonance effect is more important. All right, so extent of resonance stabilization depends on how well the lone pair can donate its electrons. We have a good measure for that, base strength, right? The more basic an atom is, the more it wants to donate electrons. So remember our periodic trends for base strength: CNOF, Cl, Br, and I. And we know that base strength increases in this direction. And when L donates its lone pair, it's actually donating lone pairs, which a measure of how important that is for L is by measuring the base strength. The more basic L is, the more it's going to want to donate its electrons. So as you can see, nitrogen here is a stronger base than oxygen. So when we have an amide, then resonance stabilization is going to be more important for an amide, right? Because the nitrogen's more basic, it wants to donate its electrons more, so the second resonance effect is going to be more important. So here's the order of resonance stabilization here. Here's everything on the next page. All right, so most resonance stabilized is going to be a carboxy group, followed by an amide, followed by OET, so an ester, followed by a carboxylic acid, followed by an anhydride, followed by an acid chloride. So the most resonance stabilized is going to be a carboxy group. And so let's do some draw some resonance structures here for these guys. And I'm going to pretty much hit the two extremes here. So we can draw a resonance structure for a carboxy group. So that's a deprotonated carboxylic acid. We see that we have two equivalent energy resonance structures. Both have identical energy. So it makes good sense here that this one is going to be the most resonance stabilized. So we have two equivalent resonance structures. So this one has the most resonance stabilization. All right, so then now let's look at the amide. We know that nitrogen's pretty basic. It likes to donate a pair of electrons here. So it's going to really want to kick in electrons. and kick those electrons up onto oxygen. So we can draw a second resonance structure here. So 2 resonance structures for the amide. Now, which of those 2 resonance structures for the amide is the most important one? The one on the top or the one on the bottom? One on the bottom. So this is, so we have definitely with the second resonance structure where there's a negative charge on oxygen and a positive charge on nitrogen, but now we have added separation of charge. So that's not as good as having something with no separation of charge. And so it makes sense that although the nitrogen does like to donate its pair of electrons, it's not going to be as resonance stabilized as a carboxy group, okay? And then, so then we can keep doing this all the way down. Let's go to the last one here that has the least resonance stabilization. And let's draw the resonance structure for that. All right, so chloride ion, very strong base. What do you think? Not a very strong base, right? So it's not going to want to donate its electrons. So that would suggest that an acid chloride is not very resonance stabilized, right? And so it's the least resonance stabilized of all of these. So we can look at basicity to explain that, and we also can look at another factor that might not be obvious. We know that chloride ion is the weakest base, but there's also something else in play here, and that's that there's poor 2p, 3p overlap. Okay, what the heck is that? So if we have an amide, we have a pi bond between a carbon and a nitrogen. Those are both second row elements. And so that would be 2p overlap. So like a carbon-nitrogen bond would be 2p overlap. Or carbon-oxygen would be 2p. When we have a chlorine and an oxygen, a chlorine and a carbon, we have a mismatch in the size. So here's 2p. And then we have 3p. This is much larger. So here's our carbon, and here's our chlorine. Over here, this would be a carbon and our nitrogen. Here's our carbon, and that's our chlorine. And if you actually look at the area that's overlapping, it's not very much. Right here is where we get the overlap, right in here and right in here. And you can see that on the chlorine, most of the electron density is far away from that overlap part. So there's not as good of overlap. Poor overlap is equal to poor resonance stabilization. So what we can say here to summarize, going this direction, increasing base strength. And then this direction, increasing resonance stabilization. So you can imagine if you replace that chlorine with a bromine or an iodine, that's going to be even worse, okay? That's going to be even worse overlap there. All right, so aldehydes and ketones are in their own category because they don't have a group L that can stabilize by resonance. So let's talk about them separately, and then we'll summarize everything. So a combination of inductive and steric effects are what we use because we don't have resonance effects here to talk about. But if you remember from 51A that methyl groups are slightly electron donating. Okay, then so that means that, again, we're going to do the same thing we did previously where we're looking at partial positive charge on the carbonyl carbon and seeing which one has the most partial positive. Partial negative. So we have one methyl that's electron donating. Here we have two methyls that are electron donating. Two electron donating methyls. So which carbon is going to be the most, which carbon is going to have the least partial positive charge? Okay, this is with the ketone, right? Because we've got two electron donating methyls. With the aldehyde, we only have one. So for inductive effect, we can just simply go, let's summarize inductive effect. Methyl is an electron donating group. That's going to make carbon less positive. Over here we have two electron donating groups, which are methyls. So therefore less positive charge on carbon. Therefore that's going to be more stable. More stable equals less electrophilic. So that's inductive effect. The inductive effect would tell us that an aldehyde is more reactive than a ketone, and that's absolutely true. And now let's talk about steric effects. Which one, an aldehyde or a ketone, is less sterically hindered? Aldehyde's less sterically hindered. So hydrogen less sterically hindered than a methyl. So in this case, the inductive effect and the steric effect are telling us the same thing, that aldehydes are significantly more electrophilic. So aldehydes are more electrophilic than ketones. Questions so far? Anybody? Okay, I don't know how well this shows up. What do you think? Compare electrostatic potential maps of the various type 1 carbonyls. So this is formaldehyde. We'll draw it right underneath in case you can't see it through the color there. This is acetaldehyde. And this is acetone. Now remember, with electrostatic potential maps, the more blue, the more electrophilic. And so allegedly, I don't know how well it shows up, but the formaldehyde with two hydrogens is definitely more blue than acetone. Does it look like that way to you, or I'm just kind of making it up? Depending on how the picture is drawn, I think it looks more blue. And it is. It's more electrophilic. So formaldehyde, more electrophilic than acetaldehyde, more electrophilic than acetone. Okay, so you can clearly see that. Let's summarize all these together. Here is the order of reactivity here. And you absolutely need to know this. You guaranteed will have a problem on midterm 1 where you're asked to rank these. Rank or pick me the most electrophilic, least electrophilic. Okay, so something like that on the midterm, and you'll likely see something like that again on the final. It's really important. It's going to help us make decisions, okay, when we get to more complicated things. All right, so acid chloride, most reactive because it has strong inductive and weak resonance. Inductive destabilizes, resonance stabilizes. So it has strong inductive, which destabilizes it and makes it more reactive, and weak resonance. So we're not getting very much stabilization from resonance. So definitely. And so because of that, acid chloride is the least stable. Most reactive. So most electrophilic of all the carbonyl compounds. And then we go to the bottom here. Amide's right above carboxylate. Carboxylate has the best resonance. Remember, there's 50% one resonance structure, 50% the other. So we have the best resonance. And so carboxylate anion is going to be the most stable, least reactive. All right, again, absolutely have to know that. That will be on the test, guaranteed. All right, so now we've talked a lot about reactivity. Now we're ready to move into talking about reactions. So in this chapter here, we're going to focus on irreversible addition reactions of type 1 and type 2. So when powerful nucleophiles add to type 1 and type 2, reaction is irreversible. So we have hydride reagents, source of H-. We'll talk about those first. And then we have organometallic reagents, source of R-. And I'm going to put these in quotes because we really don't have straight H- and straight R-. But they are sources of those. Okay, so I'm going to put those in quotes. And then sodium alkanides, those we talked about in chapter 11. So this is a source of, remember, deprotonated terminal alkynes. So these guys will also add to carbonyls. So you're familiar with that reagent, but we haven't talked about their reaction with carbonyls. But I bet most people would be able to predict what happens with that without me even telling you anything, I'm thinking. All right, so let's look at a type 1 example here. Nucleophile attacks the carbonyl. Just to remind you of the reactivity, that's addition. Tetrahedral intermediate, okay. Because these are powerful nucleophiles, they're really strong nucleophiles. They're strong bases. They can't come back off again. That's what makes this irreversible. Tetrahedral intermediate has no leaving group. And so it is therefore an irreversible addition. So since we don't have a leaving group, what we're going to end up is we're going to stop there, and we're going to add water in a second step. Add H2O or H3O plus in a second step. So what we're going to end up synthesizing using the type 1 carbonyl compounds is alcohols. And so our nucleophiles are here, H-, I'll put that in quotes because it's not really straight H-, R-. These guys are all things that can't be leaving groups. And certainly sodium alkanides. What's the pK of the conjugate acid of the sodium alkanide? Remember what that was? That was one of the ones rounded to the nearest 5. 25. So it's not going to leave, right? So that's what these all have in common. That's a typical reaction with a type 1, and then we're going to a typical reaction with a type 2 on the next page. Nucleophile attacks. Attacks the carbonyl carbon. We kick electrons up onto oxygen. We get a tetrahedral intermediate. We look at that tetrahedral intermediate and we decide, does it have a leaving group? Yeah, it does. It has a leaving group L. So tetrahedral intermediate has leaving group. If it has a leaving group, that leaving group is going to leave. So electrons on oxygen are going to come down and we're going to kick off our leaving group. All right, acyl substitution, right? If that nucleophile is one of these three nucleophiles we have indicated here, what's that compound? What is the structure of that? What category would that be? It's going to be an aldehyde or a ketone, right? It's going to be if the nucleophile is hydrogen right here on the previous page, that'll be an aldehyde. If it's R, it'll be a ketone. If it's sodium alkanide, then it's going to be a ketone that's conjugated with a triple bond, right? So because this is an aldehyde or a ketone, the reaction is going to happen again. Because we just did it right here, right? When we add these nucleophiles here, we get that. So that's what's going to happen. So we have an aldehyde or a ketone here as our product. And so the nucleophile is going to add again, just like it did on the previous page. One more time. We get a second tetrahedral intermediate. Do we have a leaving group? No, nothing can leave. Has no leaving group. Okay, so it's going to be just like this. Tetrahedral intermediate has no leaving group, so that means that we're going to add water or H3O plus. We'll just say H2O in a second step. And that's our product. So we're also making an alcohol, except this time we have two nucleophiles incorporated. That's the general thing that's going to happen for the rest of this chapter. There's some differences, and there's some special reagents that we can use where it will stop right here at the aldehyde or a ketone, but most of the time you can't. Most of the time you can't stop. Questions so far? Yes? Is the second reaction, well, you tell me. We just talked about reactivity, right? So let's go back. Let's go back and look. That's a great question. So let's see. And this is why you need to know this, right? Okay, so we have acid chloride and hydride aldehyde. So and then ketone. So if it's an ester, carboxylic acid, or amide, when we make an aldehyde or ketone, that's more reactive than the starting material. And that's one of the reasons why you can't stop. Okay, so excellent question. Yeah. So once you make the aldehyde or the ketone, it's actually more reactive here. You know, it depends on what you're starting with, whether you can stop or not. Okay? So, and we will get to that. More questions? Anybody? Yeah?
Could you just use an excess of the reagents to prevent it?
No, you can't. And we'll get to that. There's some special reagents that you can use to stop, but I understand that they don't work very well. So we'll talk about it when we get to them. And there's ways around that. So what I want to do right now is I want to talk about hydride reagents first, and then I'm going to talk about the other kinds, organometallic compounds. So nucleophile addition of hydride to the electrophilic carbon results in reduction of the carbonyl group. Okay? So what's happening here? Boom. I have it in quotes because hydride by itself doesn't work in this reaction. So can you do this reaction with sodium hydride? No. Can't do this reaction. Sodium hydride does not add to carbonyls. So we have special reagents that do. Then you do the addition, and then you add water or acid in the second step. And as you can see, we've actually reduced the carbon-oxygen double bond. So the reagents that we will use, sodium borohydride, NaBH4, lithium aluminum hydride. You're also familiar with that. No sodium hydride. So sodium hydride only acts as a base, not a nucleophile. So seems like it should work, but it doesn't work. So the reagents that we're going to see, sodium borohydride, lithium aluminum hydride, and some other special ones that we will encounter as we go along in this chapter. All right, so these two hydride sources behave very differently. And maybe if we draw the structures, we can figure out why that is. So sodium borohydride has a boron-hydrogen bond. Lithium aluminum hydride has a aluminum hydrogen bond. And one of the ways that we can predict the reactivity, the relative reactivities of these two compounds is to look at electronegativities. And so we see, let's see, we have for boron 2.0, hydrogen 2.2, aluminum 1.6, hydrogen 2.2. All right, so for both of those bonds, we have a polarization. We have partial positive charge on boron, partial negative charge on hydrogen. So electron-rich hydrogen. Notice this is the opposite that we see with an acid. With an acid, we have partial positive hydrogen. So we have partial positive on aluminum, partial negative on the hydrogen. Which one of those bonds is the most polarized? Yeah, lithium aluminum hydride. And so lithium aluminum hydride, there's the most partial negative charge on hydrogen, so it's a more reactive form. So sodium borohydride is much weaker than lithium aluminum hydride and reacts slowly with water. And this reagent only reacts with aldehydes and ketones. Lithium aluminum hydride, as you can see from the polarization of that bond, it reacts much, it's a much stronger reagent, reacts violently with water. You have to use dry solvents, you have to use dry glassware, so you pre-bake your glassware or you flame dry it. You use dry solvents and you quench very carefully. The quench is addition of water after the reaction is done. So that's what we mean by quench. Addition of water after reaction is done. I had an explosion with lithium aluminum hydride when I was in grad school. One of the things that lithium aluminum hydride is used for is drying solvents. So if you add a solvent to lithium aluminum hydride, it will suck up all the water, and then you distill your solvent over. And I was distilling a solvent in grad school over lithium aluminum hydride. And I walked in, I had it going in my hood, and I lowered the lab jack to stop it because it looked like it was done. And I saw that I still had a little bit of solvent left in the bottom. I wanted to go a little further, so I rolled back up the lab jack so it was still heating, and I closed the sash, and I took 2 steps, and the whole thing exploded. So I would have had my hand in there like seconds earlier. So it's very violent reaction. So one of the things that I'm a stickler for is if you're using lithium aluminum hydride, don't combine it with water. If you don't number those steps, you're gonna miss the points, okay? Because it reacts violently with water. So if you added water to, so when you do a reaction with lithium aluminum hydride, you cool it down and you put it in an ice bath, and then you add 1 drop of water, and you'll see, hydrogen gas coming off. and then you let that cool, and then you add another drop. So what I'm saying, don't mix lithium aluminum hydride and water together, okay? Sodium borohydride, on the other hand, reacts slowly with water, so it's a much milder reagent, but it's also not as powerful. So the lithium aluminum hydride reacts violently, and it's going to react with all type 1 and type 2 carbonyls. Reacts with all type 1 and type 2 carbonyls. So kind of cool to be able to predict that reactivity just by knowing some electronegativities. And it does exactly what you would expect it to do. I do want to label this, so when you come back and see that later, you'll know what we're talking about here. So here, greater concentration of negative charge on hydrogen. Therefore, it's going to be more reactive. And what we're going to see is when we start talking about the organometallic reagents is we can make the same predictions that we did here just based on electronegativities. All right, so here's a typical reaction with type 1 carbonyls. So good news, you're familiar with lithium aluminum hydride from 51B. That's one less reagent you have to memorize, so hopefully it's already in your head. And what we did with the lithium aluminum hydride in 51B is we had it attack epoxides, right? That was something that we did in 51B. All right, so the arrow comes from one of the 4 aluminum hydrogen bonds. Take your pick. It's going to attack the carbonyl. We're going to kick electrons up onto oxygen. So addition of hydride. To sp2 carbon. Now it's a little easier to see. Now that we're using real reagents rather than just NU generic, do we have any leaving groups on this tetrahedral intermediate? Hydride can't leave. pKa of the conjugate acid is 35. Methyl can't leave. pKa of the conjugate acid is 50. Okay, so those are not going to leave. So our tetrahedral intermediate has no leaving group. So as much as possible, I want to encourage you, rather than memorizing products, to actually go through the process of seeing what the reagent does and being able to make decisions. And then if I give you something that you haven't seen before, you'll be able to get the answer easily, okay? So at tetrahedral intermediate, we say that, of course, because it's sp3 now, has no leaving group. And it's also, so therefore it's an irreversible addition. All right, so that means it's going to stop here until you add what? Water? Water or acid? In a second step, okay? And so then once you add water, if I ask you the mechanism for this on midterm 1, you would just simply show the protonation of the oxygen. So that's going all the way back to chapter 2. All right, result is reduction of the carbonyl. How do we know it's a reduction? We we lose the loss of carbon-oxygen, gain of carbon-hydrogen. So we talked about how to figure out whether you have an oxidation or reduction. That was back in chapter 12. So if you don't remember that, you can take a look. Okay, so therefore a reduction. All right, similar reaction occurs with type 1 carbonyls and sodium borohydride. Virtually the same reaction. This thing is much more touchy than the one in the other room. Going to have to get used to that. So sodium borohydride, right? Arrow comes from one of the boron hydrogen bonds. We attack the carbonyl carbon. We kick electrons up onto oxygen. Notice with sodium borohydride, we're going to actually protonate with ethanol. They don't have to be in separate steps. They can be mixed together. Okay, so you don't have to number it with sodium borohydride. Again, tetrahedral intermediate has no leaving group. And that's because the hydrogen that we just added can't come back off again. So this is the hydrogen that we just added. This can't come back off because it's a terrible leaving group. So can't leave. Therefore irreversible. All right, and then in the second reaction here, here we don't have it as a second step. It is actually in the same reaction vessel. And I'm just, like I said, this thing is a little bit different. I'm going to have to get used to it. HOET, right? So we actually protonate with ethanol, which is the solvent that you use for this reaction. Questions? Anybody? So how do we do this? How do we reduce aldehydes and ketones back in chapter 12? Do you remember how we did that? Hydrogen and palladium. That's not the most common way to reduce aldehydes and ketones. These are the more common ways. So that's not very common to do that in chapter, like we did in chapter 12. This is the more common way to reduce a carbonyl. All right, so that's what happens with type 1. Let's do type 2. Do we need to talk about sodium borohydride with type 2? No, because it only works on aldehydes and ketones. So we're done with sodium borohydride. All right, so lithium aluminum hydride, we can do this, right? We're going to go through here. One step at a time. Rather than just predicting products, memorizing products, having a whole sheet that you memorize, we're going to go through the thought process. Lithium aluminum hydride, very powerful nucleophile. Arrow comes from the aluminum hydrogen bond. We attack the carbonyl carbon. We kick electrons up onto oxygen. Addition. All right, so let's analyze our potential leaving groups. Certainly methyl can't leave, hydrogen can't leave. What about methoxy? Okay, yeah, it actually can in this reaction. And we'll talk about why that's allowed here. That wasn't a leaving group in an SN2, right? But we can actually have it leave here. So what I told you is in chapter 7, if you had my class, I said methoxy can't ever be a leaving group in an SN2 reaction. can't ever be a leaving group, but we're going to have exceptions. Of course, this is not an SN2 reaction. We're going to have exceptions, and I'm going to bring them up as they come along. So this is exception number 1. So we know that methyl certainly can't leave. Methoxy, what's the pK of the conjugate acid of methoxy? What's the pK of methanol? Rounded to the nearest 5 is 15, right? Shouldn't be a leaving group, but it's okay in this case. So this can leave. All right, so what we're going to have is elimination here. So notice what I'm doing in my arrow pushing. I put lone pairs on all the reacting species. If the oxygen's reacting, I have all of its lone pairs. If the methoxy group is leaving, I have all of its lone pairs. All right, so let's see what we get after that step. Addition, elimination. And that's what we'd expect for type 2. All right, what do we know about reactivity of an aldehyde versus an ester? What's more reactive, an aldehyde or an ester? Aldehyde's more reactive. Okay, so aldehyde's more reactive, so we can't stop here, can we? So this is more reactive than an ester. Therefore, we can't stop here. So what's going to happen is the lithium aluminum hydride is going to add again. Let me draw it up here where I have a little more room. It's going to add one more time. Now we're going to get addition only. Why? Because that's a type 1 carbonyl. It doesn't have a leaving group. But in case we didn't notice that already, let's just draw the product, the tetrahedral intermediate that we get, and see if we have any leaving groups. We certainly do not have any leaving groups. Hydride, 2 hydrides and a methyl can't be a leaving group. So tetrahedral intermediate has no leaving group. Therefore, stops here. Until you add water in a second step. So step 2, H2O. Then we protonate our alcohol. We protonate our alkoxide to get an alcohol. Questions on that mechanism, anybody? Possible mechanism for midterm 1. All right, so you're very upset, I can see that, by the fact that we have alkoxide as a leaving group. Let's explain why we're allowed to do this in this case here. We couldn't do it in an SN2, but we can do it here. Let's compare. In an SN2 reaction, so this again was chapter 7. Chapter 7, nucleophile, we said this can't happen. So this doesn't work. So we'll draw it and then we'll put a big X through it. So that would be backside attack, having alkoxy as a leaving group. And what you'll notice is that the product and the reactant have a similar energy. Product and reactant have similar energies. So we're not doing anything to dramatically change the stability of this atom by doing that SN2 reaction. We are, on the other hand, in this reaction here, we are dramatically changing the reactivity, because if we have these electrons come down and kick off from a methoxy group, we're getting an aldehyde. Aldehyde's much more stable. The carbon-oxygen double bond, very powerful double bond. And so in this case, the aldehyde is much more stable than the tetrahedral intermediate. We also had an alkoxide as a leaving group one more time already. Chapter 9, right? What reaction was that, where we had an alkoxide as a leaving group? Anybody remember? So I apologize. This was our second exception. We had a first exception in Chapter 9. How about opening up an epoxide? Might not notice that. Wow. When we do this reaction, we are actually having an alkoxide as a leaving group. It happens to be in the same molecule. It's attached to the molecule, but we do have an alkoxide as a leaving group. And we talked about the fact that this was allowed and why it was allowed last quarter. But make no mistake about it, and this is an SN2 reaction. So as you can see, we sometimes break these rules that we have in chemistry when we have something going to something much more stable than what we started with. And so again, product is much more stable than reactant, because we've relieved that ring strain. Questions? Anybody? All right. Important points about hydride addition to carbonyls. Remember, sodium borohydride is not powerful enough to add to type 2 carbonyls, so just aldehydes and ketones for that one. Lithium aluminum hydride adds twice to esters, even if only one equivalent is used to stop at one addition. Use a reagent called diisobutyl aluminum hydride, or DIBAL. Here is our abbreviation right here. And you feel free to use the abbreviation. It's stronger than sodium borohydride, but less reactive than lithium aluminum hydride. It's used exclusively to reduce esters to aldehydes, and it doesn't work very well, right? It just really works loud. Any TA I've never done the reaction, but any TA I've ever had said that's a really lousy reaction. It doesn't work very well, so I'm going to give you an alternative that you might like better. If you don't want to memorize DIBAL, let me show you what this looks like. So diisobutyl, remember what iso means. We have a branch on the end of the chain. Diisobutyl aluminum hydride. Different than lithium aluminum hydride because we don't have 4 groups around aluminum, do we? What would we call that when that aluminum only has 6 electrons? What would we call that? Two names we would possibly call that. Maybe even from back in GChem. Now we're really going back. As we call it open shell or Lewis acid, right? So, and we have an oxygen here that has lone pairs, so the lone pairs on oxygen are going to want to attack that. That's the first step. But we'll stop right there, and you guys are just going to have to wait till we come back on Monday. I hope you have a great weekend.